let's proceed. So the point here is that, by manipulating the percentage of, water and organic solvent percentage, by manipulating, the ratio of water and organic solvent, you can decrease or increase the retention time. Okay, so you can change the retention time of your compound in the column, right? So if we come back to like this slide, so here are some features of the chromatogram. So basically, shorter retention time. If your compound has a shorter retention time in the column, the peak in the chromatogram tend to be sharper. They tend to be sharper. But again, a shorter retention time tend to, it means like, the separation efficiency is, not as good as it is when you have a longer retention time. Okay, so the first feature is that the peaks is gonna be broader as the time increases. For example, peak B is broader than peak A. And that's because of the random diffusion process in the column. So second, a typical chromatogram is the symmetrical nature of all eluting peaks. So here comes the example. A symmetric nature means that it's when you cut it into half, the right-hand side one is the mirror image of the left-hand side. So we call it symmetric. Okay, so typically for a chromatogram, a peak usually is a symmetric. We call it Gaussian distribution. Okay, but in reality, if your column is aged, or let's say you used for a long time and the column is impaired by the junk or other reasons, from time to time you will get a skewed peak. A skewed peak means that it's no longer symmetric anymore. It becomes skewed. For example, it might look like this. The peak might look like this. Okay, it has a long tail. Okay, and we usually see this kind of phenomenon in aged column. Okay, so after introducing two of the basic terms related to chromatography, there are a few factors related to chromatography that I want to introduce in this lecture. There are actually 4 factors, relevant to chromatography. So this is just the theory related to chromatography, and you guys need to know that. 所以我接下来要讲的就是几个影响，不是影响啊，就是我们在讲这个 chromatography 的时候呢，有时候你会看到这几个名词，那大家要知道它是什么意思，那还有它背后的理论。Okay. So the first factor, we call it distribution constant. Distribution constant. So the distribution constant is actually a partition coefficient. So we have been talking about partition coefficient like all the time. And basically, a partition coefficient reflects the relative affinity of your compound in two phases. So distribution constant or partition coefficient is the concentration of solutes in the stationary phase, which is denoted by CS, divided by its concentration in the mobile phase, CM. Okay, so Kc is equal to Cs over Cm. Well, and let's take a micro view here. So let's say in this column, you have samples injected and you leave it there. So after reaching equilibrium, okay, some of the compound will be solved on the surface of the solid material, and some of that will stay in the mobile phase. Okay, so the Ks is the concentration in solid phase over the concentration in mobile phase. Okay, so what's the relevance here? Well, if you look at this example, in the case A, when we use water as mobile phase, or use water as a mobile phase, versus the case that we use 50% water and methanol as like mobile phase, in which scenario you have a large Ks. So this is a case A and case B. So in which case you get a large Ks? Remember, Ks means the after reaching equilibrium concentration of your compound in solid phase over the concentration in mobile phase. So case A or case B, in which case you get a large Ks. Well, something we want to keep in mind is that large Ks means that the retention time for your compound is gonna be longer. Okay, large Ks because it has higher affinity with the solid phase, right? So it's gonna have longer retention time. Okay, so back to this question, which one has a large Ks? Case A, right? Because the affinity of compound A in water is lower compared with the affinity of compound A in this mixture. Okay, so here is the first point. If you increase the solvent in the mobile phase, you are going to decrease the Ks. Decrease the Ks means reduce retention time. 我一直在讲就是上升下降，上升下降，这个大家可能会有点搞混哦。但这个 case 就是他们这个 compound 对固体相跟对你的动向就是意向的相对的亲和力。对，那你现在这个 compound 对于这个 solid phase 的亲和力远高于对水的亲和力，那代表这个 compound 就是会被这个 solid phase 给黏住啊，所以它在移动的时候就移动得很慢。所以这个 column 要跑出这个compound 要跑出这个 column， 然后被 detector 侦测到的时间是不是要很长，对吗？那所以如果你今天把你的动向里面的 organic solvent 的比例提高，那你是不是增加的这个 compound 对于你的动向的亲和力，对吗？所以这时候你的 Ks 就下降。那 Ks 下降代表什么意思？它在流动的过程中就会跑得比较快。Okay. So that's the first term. That's the first term. So the larger Kc means the more the solute would be solved or partitioned in stationary phase. And that means the longer it is retained on the column. Oh, by the way, this is the basically the 4 weeks after I caught a flu, so it's supposedly not contagious. So you guys should not be worried about it. 这是我第4周感冒了，所以基本上应该就是完全没有感染力了，所以大家不要那个太 freak out。好，So Kc again is dependent on the types of stationary phase and mobile phase. And the separation would be impossible if two compounds have the same Kc values. Okay, so so one of the example for two compounds have the same Kc value is given here. So for example, isomers, this compound and this compound, they are structurally very similar to each other. You can see that, but they are like stereoisomers. Okay, the only difference is that this is a trans or cis, and this one, another one is trans. So they are structurally, very similar to each other. And in this case, they tend to have very similar Kc. So making them very difficult to separate using chromatography. Right. Okay, so that is the first factor, distribution constant. So the second factor related to chromatography is actually retention factor. So the definition of retention factor, from the wording, retention factor is related to the compound retained in the column. Okay, so retention factor is defined as the ratio of the time an analyte spends in the stationary phase to the time is spent in the mobile phase. Well, it sounds a little bit confusing here. So what does it mean the time is spent in the mobile phase? Well, let's look at the practical meaning here. K, retention factor is K, which is equal to your target compound, the retention time of your target compound, TR. Okay, for example, for compound A, TRA is the retention time, right? Minus the TM. TM is the retention time for this peak. So as I mentioned in previous slide, TM is the compound that has no affinity with the column. And the time represents the traveling time required for the compound to escape the column. Okay, TM is the compound whose affinity with stationary phase is 0. Okay, so the time difference here on TR minus TM over TM. So we call it retention factor, or retention factor. So large K means what? The compound has high affinity with stationary phase or have low affinity with the stationary phase. Large K. Well, let me put it in this way. So compare with compound A and compound B, which one has a large K? Which one has a larger K? A compound B, right? A compound B. So based on the chromogram here, compound A has a high affinity with the stationary phase or compound B. Oh, compound B, right? Because the retention time is longer. So basically, large K, large retention factor, a large retention factor means high affinity with the stationary phase. Okay. So when it comes to the chromographic method, an ideal separation of solutes in a mixture can be achieved if the K values lie in the range of 2 to 10. So this ideal K would be around 2 to 10. If it is larger than 20 to 30, then that means it's too long. Okay. If the K is larger than 20 to 30, or even 40, that means it's too long. You need to modify the method. Why? Why? Why do we care about, the retention factor too large? Or why do we care about, the retention time too long? Well, the hint is here. Why? 为什么我们就是在建立分析方法的时候，这个 retention time 太长不好，太短也不好啊？为什么太长会不好？The hint is given in this slide. Remember, as you have longer retention time, the peak shape is gonna be broader. Okay, it's gonna be broader. So imagine that you have a super long retention time. At the end of the day, the peak shape will look like a slight hump. So at the end of the day, sometimes, frequently in this case, you might get a very smearing like peak shape, and which make you difficult to do the quantitation. Okay, so here comes my question again. If you get a really, really long retention time, how do you do? In the case of liquid chromatography, what can you do to like shorten the retention time of your compound? You need to increase the solvent ratio in the mobile phase. 大家有懂吗？就是如果你要缩短它的 retention time 的话，是不是去提高这个动向里面的 solvent 的浓度，增加这个 compound 在 mobile phase 里面的 affinity， 然后它就可以比较早被引流出来。All right. So the third factor and the fourth factor are semi-relevant. So they are pretty similar to each other. The third factors I'll be talking about is a separation factor. So from the wording here, separation factor means it's related to, the efficiency of your column to separate two peaks. The column efficiency to separate two peaks. Okay, so we define separation factor as the ratio of distribution constant of two solutes. Okay, again, distribution constant is K. K is Kc. So the distribution constant of two solutes, and it can be derived in terms of the ratio of the retention factor of two solutes. For example, if we are focusing on compound A and compound B, how well they are being separated. How well they are separated, we can use alpha to rationalize it. 这边这个 separation factor 就是在探讨，就是你这个分析方法或者这个 column， 它对于你这两个 compound 特定的这两个有兴趣的 compound， 它们的分离程度到底是好还是坏？好，我要再提醒大家一次哦，就是这个我们 chromatography method 最重要的就是用来分离 compound 而已，所以其中有个 factor 会来用来有两个 factor 啦，就是下一个也差不多哈。这个 factor 用来描述它们到底被分离的好不好。Okay. So practically speaking, alpha can be calculated by the time differences of the retention time of your target compound and retained peaks. So TRB minus TN over TRA minus TN. Okay, so something we want to keep in mind is this: alpha is always larger than 1 because we put the shorter retention time 1 in the denominator. Okay, we put the shorter retention time 1 in the denominator such that alpha is always larger than 1. So subscribe A denotes a rapidly eluted chemical with a weak retention factor, so that alpha is always greater than 1. So for compound A and compound B, if you get a retention factor of 1, what does it mean? If you have a retention factor of 1 for compound A and compound B, what does it mean? That means these two peaks are totally overlap with each other. Okay. So it's a term to describe how difficult it is to separate two solutes. If you have a factor of 1, that means, okay, they are inseparable. You won't be able to separate them. So two compounds can be separated only if a higher than 1 in the select phases. So for HPLC, separation should be like 1.05 or higher. 1.05 or higher. Okay, so this is separation factor. And to calculate a separation factor, all you need to have is the retention time of each peak. Okay, retention time of each peak. But the next term we are going to introduce is resolution. Okay, so this one is basically, I think it's pretty important. It's pretty important. So resolution R, or resolution R, it's a term or is a factor to show you a column's ability to separate two peaks. A column's ability to separate two peaks. So it's similar to separation factor, pretty similar. But in the case of separation factor, we only consider retention time of each peak. Okay. So let's say we have two cases. In case A, the peak look like this. This is the peak A and peak B. Okay, this is the TA and TB. And in the second case, again, we have T and TB are identical. So TA and TB in these two cases are identical. So in these two cases, they have the same separation factor, right? Because the only thing we care about when it comes to the calculation of alpha separation factor is the retention time, right? But if you look at these two cases, which one has a higher ability to separate these two peaks? Well, we'll definitely say case A, right? Case A, because a case A, like the shape is narrower. So resolution is a more comprehensive factor to show a column's ability to separate two peaks. And in the calculation of resolution, it takes into account of the width of the peak. So you can see that the R, when it comes to calculating the R, the numerator represent the differences in terms of their retention time, or TRV minus TRA, and the denominator is the width of the peak A and the width of peak B. So it's the average width of the peak A and peak B. So when the width of the peaks are taken into account, you can better reflect the true ability of column to separate two peaks. Okay, so here shows a typical example of peaks featuring different resolution. For example, if you have an R of 0.5, they kind of merged. They merged. So peak A and peak B merged, and eventually you are able to you're only able to see a single broadener peaks. But if you have a resolution of 1, like the area they overlap is like 2.3%. And for R of 1.5, basically they are only 0.1% area overlap. Okay, so typically to successfully separate two peaks, R of larger than 1.5 is needed. Okay, it's needed. Well, I have a complementary slides in 44. Yeah. Okay, so this figure is adapted from the user guide of column. So here it shows that for a column, for the same column, usually they provide different thickness of the film. So over length. So in these three cases, you can see that if the column length is 15 meter, if the column length is 15 meter, the R for these two compounds is going to be like 0.84. Then if you use a column with a length of 30 meter, got better separation efficiency. You can see, for the same group of compound, the R becomes 1.16. Then if you further doubling the column lengths, it get much better separation. So in this case, the R become 168. Okay. So does it make sense? What is the take-home message here? Well, basically, the longer the column, the better the separation. Okay. The longer the column, the better the separation. So this is an example demonstrating, what the R is. It show you, how good the separation is. So next time, if you check the user guide from a column and you see a R, you should be able to know what it is. Okay, that's the key points. 所以大家如果就是以后就是有机会用到这个程式管注上面，它都会跟你讲说这个 R， 或者是待会要讲的有个东西叫 plate number，大家要知道它们是什么东西。好。All right. And so after talking about the 4 important factors related to chromatography separation, the next terms I want to introduce is a theory related to chromatography. So this theory is number of theoretical plates, a number of theoretical plates. So sometimes we use N as the number of theoretical plates, the N of your column. So N, or number of theoretical plates, is actually an index that indicates column efficiency. Again, so N represent the column efficiency. But what is column efficiency? 什么叫做管住的效率？ Okay, the definition of column efficiency is the ability of column to produce narrower picks. The ability of a column to produce narrow pick. Column efficiency means the ability of column to produce narrow pick. Okay. So for chromatography, the narrower the pick is, the better. Okay. That echoes what I said in previous slides. You want to avoid like super long retention time because the pick become broader. Okay, broader means it's gonna make you difficult to do the quantitation at the end of the day. So the narrower, the better. If something we want to keep in mind is that from a chromatography, the narrower the pick is, the better. Okay, and so the number of theoretical plates describe the number of plates as defined according to plate theory. I'm not going to a detail, but this theory, the inventor of this theory, eventually, I mean, at the end of the day, he won a Nobel Prize because of this theory. So it's pretty useful, I guess. And you know, the theoretical plate number can be used to determine column efficiency based on calculation in which the larger the theoretical plate number, the sharper the picks. So here comes the point. The larger the theoretical plate number for a column, that means the column is able to produce narrower peak. Okay. So when it comes to calculation, we may use this like equation. So for example, for this peak, so the plate number for this column can be calculated using this like equation, and TR is the retention time. TR is the retention time. W is the width. The width. Here. W. Pick width. Pick width. And you got square. Okay. So a column with more theoretical plates would have greater resolution power, and for GC, an efficient column should have a plate number larger than 10,000. Okay, so that's a brief introduction of a number of theoretical plates. So let's look at the supplementary slides. I guess it's 40. So the theory behind, like, the concept behind the theory is that, for a column, it can be like the plane model supposed to let the chromatographic column contains a large number of separate layers. So we call it separated plates. And this separates equilibration of the sample between the stationary phase and mobile phase occurred in these plates. And the analytes moved down the column by transfer of equilibrate mobile phase from one plate to the next. Well, these are the key contents for the plate theory. But anyway, that's not the points here. So let's look at this one, these slides. So, well, if we look at this table, oh, by the way, this is the content I borrow from the internet, from Agilent. So Agilent produces a lot of gas chromatography column. So specifically for this column, they have different diameter. Okay. So for this column, the coating material is the same. The difference is that the column diameter is different. Okay. So here comes the first point. If you look at the column ID, ID means inner diameter. When you have larger inner diameter, you have lower theoretical plate number. What does it mean? Lower theoretical plate number means the capability of the column to produce narrow peak is weaker. Okay, so anyway, the larger the number, the better the efficiency of the column. Okay, so from this table, you see that as you increase the inner diameter of your column, you lower the theoretical plate number. Okay, so well, it says that column efficiency is inversely proportional to column diameter. So which echoes what we found here. As you increase the column diameter, you decrease the plate number. So if we compare these two, like a chromatogram, for these two compounds, if you use this column, a column with 0.5 millimeter inner diameter, versus you use this column, which features a 0.3 millimeter as an inner diameter. So which one is going to have a better separation efficiency? Or which one is going to have a better capability to produce sharper peaks? Which one? Based on this table, the smaller the inner ID, the one with a smaller inner ID, inner diameter is going to have a higher capability to produce sharper peaks. So that's true here. You can see this. For this column, they got better shape. They got better separation efficiency. Does it make sense? Okay. Well, so there will be a brief introduction of the theoretical plate number. So, again, if I use this figure as an example, so let's say we have three columns, and the coating material is the same. The coating material is the same. The only difference is that their inner diameter are different. Okay, so we have column 1, column 2, and column 3, column 1, column 2, and when we inject the same target analytes into these three columns, they generate a chromatograph like this. So based on this result, which one has a higher theoretical plate number？ 所以大家看这个图的话，大家就是很明显的哪一个是有比较高的，哪一个 column 会有比较高的 theoretical plate number？ 记得哦 ，theoretical plate number 代表一个 column 的 efficiency。column efficiency 越好，代表它能制造出来的 pick 的，就是越 sharp， 越窄越 sharp。那哪一个 column， 所以哪一个 column 它的那个 plate number 比较大，比较 sharp 那个什么，所以是 column 1。然后接下来 column 2， 再来 column 3。So we can see that the theoretical plate number for column 1 is like 10,000, followed by column 2, which is 3,500, followed by column 3, which is 2,000. Okay, it makes sense. So the column with the highest efficiency will deliver the highest and nearest peak, which is column 1. And the column with the lowest efficiency exhibit the widest peak and lowest peak heights. And another important feature here is that, when you are doing the integration for these 3 peaks, the peak area should be equal. That should be pretty comparable. That's another feature. So although peak 3 is broader, but if you do the integration for the peaks, the peak area for these 3 peaks should be identical. 好，我再强调一下哈，这个是 chromatography 另外一个特性。好，如果你现在用三个不同的 column， 然后你注射同一个样品就代表它们这个 target analyte 的浓度是一样的。好，打进去之后呢，虽然它们的 peak shape 不一样，但是如果你去做积分的话，这3个积分出来的面积会非常相近。OK， 这个 peak area 比较 broader， 并不代表它的 peak area 会比较低，积分出来会是一样的。这是 chromatography 另外一个特性，大家要注意一下。All right. So here comes an example that I adapted from the textbook. I'm gonna leave it to you guys. You can find the answer from the textbook, and this one is relatively easy and pretty straightforward, and it might show up in your final exam. Okay, so put some effort to like go through it and figure out. All right, so far I have been introducing the key terms related to chromatography. Not only limited to gas chromatography or liquid chromatography, but for all kind of chromatographies. Okay, so loss vectors can be used for different kind of chromatographies, including liquid chromatography, gas chromatography, and ion chromatography. Okay, so from now on, I'll go ahead and talk about the details and the key components for each chromatography. I'm going to introduce the key components and the working mechanism, how it works for different chromatography. And the first one I want to talk about is a gas chromatography. So as I say, for gas chromatography, the driving force is gas. So you need to have a gas to push your target analytes and other compounds to move forwards. So when the your compounds and your target compounds and other background matrices moving forward through the column, they would be separated because of the affinity, because of the differences of affinity with the stationary phase. Okay, so when it comes to gas chromatography, one of the key components would be a gas supplies. So for gas chromatography, usually it comes with a gas tank, a pressurized gas tank. So it provides the driving force. Okay, so following the gas tank, we'll have a regulator. A regulator 就是控制阀的意思哦，可以去调整气阀的那个气体出流量。So we call it a regulator. 那个气阀叫做 regulator. Okay, and then come up with flow controller. So eventually the gas will go into GC. So here, this is the central component of a gas chromatography. So in a chromatography, you have three things. The first one, four key components. The first component is the oven. As denoted by the black box. It's an oven. So oven is used to control the temperature in these environments. Okay. Again, gas chromatography, one of the key components is the oven. And the function of oven is to control the temperature. Okay. Inside the oven, you have a column. Okay. So column is used to separate the compounds in your environmental sample. Okay. So you see that the gas supplies is connected to the column. Okay. And apart from column, you have a sample injector. That's where you inject your environmental sample. Okay, that's where you inject your sample. So when you inject your sample into it, the gas the gas suppliers supplies the gas to move your compound, going through the column. So your target compound can be separated from other background matters. Okay, and at the end of the column is connected to detector. Okay, connected to detector. Detector is something that you use to quantify your target compound or other compounds. Okay, and connected to a detector, usually you have a computer to collect a signal. So that's the key components for a GC system. Well, here comes my first question. Why do we need to have an oven to control the temperature of your column? What's the purpose of controlling the temperature of your column? And the second question is that how do we inject our sample? Okay. Those are two questions that I have for you guys. So after taking a short break, let's come back and then to figure it out together. All right. So I'll see you guys in 10 minutes.